So where we were just before the break is that we start looking at this monopole. And the monopole antenna is an antenna that sits above a ground plane. And a ground plane is a big conducting object. So in the ideal case, it's what says here, like an infinite PEC plane. So infinite, which means extent in this XY plane, and perfectly electric conducting. So that's of course an idealization of a real condition. But if you have, for example, a metallic part of a car or a boat or something, that typically works like a ground plane. And as long as this is fairly large compared to your antenna, yeah, you can treat it as this infinite one, at least in the first approximation, which gives you quite a lot of understanding. And in many cases, we can even treat the ground in the first approximation as a good big ground plane. So it gives a very easy way of doing things. And what happens here is that if we now have these cases that we say that you have your a current density, and if we can start with the current density that I say here, which I call horizontal. So it's parallel with the ground plane. What happens now is that we can remove the ground plane, and then I will have added one current that goes in the opposite direction below it. So the distance between these two are the same. So if this is at height d, this one here is at distance d, and this one is at distance d. But they go in the opposite direction. So it looks like we can then take away the ground plane, and that is what you can see here. That means that there is no ground plane anymore. And the radiation above the ground plane, then I need to sum the pieces that come there. So I need to take this first, and then I need to take plus this one second here. And I get radiation from both of them. So if I want to know the field up here, the E field, I get one from this one, and I get one from this one. I have to add them both. Below the ground plane here, the electric field is 0 because nothing radiates below the ground plane. So that's one way of really using these ground planes. An interpretation to this, if you think about the communication system or something, you could say that you have your, what to say, this one, it radiates some wave, it hits the ground plane, and then it gets reflected up and it comes to the receiver here. That means in the receiver position, I will add the component that comes this way plus this one. So I will add both. And I get this multipath propagation. And that is the same thing I do if I look now in the picture here where I have removed the ground plane, because then you get this one, we call this 1, and I call this 2. You get the same radiation there. And then I have to add this one. So this is my 2. And what I've done here is in some ways that I've taken the original one, which was this dashed line, and I replaced it with the one that sits down. And that simplifies the things, because then I don't have to deal with a ground plane, reflections, and so on. I remove the ground plane and I get 2 radiating sources instead. And that's one way of saying what we do with these image currents. The case I showed you first here, yeah, that was the horizontal one. If I do the same for the vertical ones, yeah, then I take this one and I replace it with this one plus this one. And here they go in the same direction. And now you can start asking the question, okay, why does one go opposite direction? Why is one in the same direction? What is a good way of understanding this and remembering these things? So if we take this, it actually goes back to a ground plane. If I say here, it says a charge. If I do a plus charge there, then I always get an image current here, which is minus Q. So instead of a current, if you do a charge, currents are charges that are moving. Then I get an image current that is minus of that one. And now we could say that you had 2 of these. So let's add another one. So let's add one there too, and that is then minus Q. Then that minus Q will be something sitting up there, and that is then plus Q. And what you can see in this case, if you now say that the current is from minus to plus, it means this one is going from minus to plus there. It goes from minus to plus there. These arrows are in the same direction. But if I do the same thing and I do it now with a different color, so I take the next one and I do this minus q there, then I should do this one here, and then I have a plus q there. And if I do the same thing, that I say this one is from minus to plus, it goes in this direction. And if I go here again from minus to plus, then I go in this direction there. And here I can see I go with my arrows in opposite direction. And that's an easy way of understanding why horizontal currents change their direction. Vertical currents do not change their direction. That's one way of knowing it. I can give you another one, which is basically as simple to understand this. And that is if you take your horizontal currents as you have here, and let's say you put them just on top of the ground plane. What happens if you put a current on a big ground plane? You short circuit that current, which means that you replace that with a current that sits like there, and actually the sum of these two are zero, because they go in the opposite direction and they're very close to each other, which is a thing you should have if you put a current on a good conductor. It gets short-circuited, so it should disappear, which also makes sense then that the horizontal currents short-circuit each other, so they cancel each other. They have to go in opposite direction, while vertical do not change. So that's one way of understanding why we have this effect of these ground planes, or these image currents when we remove the ground plane. And having these image currents is a really powerful technique to analyze these cases, because then we can see it as one new antenna. We can soon see it as an array antenna, and we can analyze what's happening with these cases. We will come back to these cases in many situations and many different types of antennas. For example, the antenna you build is a patch antenna. It sits on a ground plane. And also there, we need to understand what happens with image currents when we remove one piece from it. So now we should do then the monopole. So the monopole antenna was this then half dipole that sticks out of the ground plane. So let's assume that it's half a wavelength. It doesn't have to be, but let's assume that. So if I have my dipole to start with, then I have my dipole antenna here. So we will have a typical length of this L. And then we can have a current that goes down there, and we know it's resonant when it's half a wavelength. And then I look at my monopole antenna. Yeah, then what I had here was just a current that came there. What I have to add is the image current, which is then the current that should be down there. And that is what I've drawn in the case of the dipole. So the removed part of the monopole forms in some ways the dipole when I added the image currents. So that means that when I would like to know the radiation here from the monopole, I want to know what the electric field is somewhere here. Yeah, from the monopole, I have the current, or the current that sits here on the top of it, but I also have to add the pieces that comes from the image part of it. I have to sum up both of them, and that means that I get this, the cases with the dipole. So when I look at the radiation pattern of this, yeah, it's basically the same above the ground plane. But again, I will get something with powers that start changing here. So I have to analyze a little bit in detail to understand what happens with the directivity, for example, when I go from the monopole compared to the dipole. And the same as the folded one, what happens with input impedance. But the first big thing is that the monopole is really half a dipole, where you just remove the radiation below the ground plane. So you replace the lower part of the dipole with, in some ways, this image currents that's formed from the monopole. So if you now ask again, what's happening in these cases? So we make a small poll here again, and we ask now the question here. This image current, what does they show? They show that the maximum directivity of the monopole is A, same as the dipole, 2 times the directivity of the dipole or half the directivity of the dipole. What do we get from these cases? And just understanding it again, what we have in this picture is that the monopole, yeah, you have the current that sits up there. To get out here this case, so you get what radiates from it, you add the image current, you get the dipole. And then you ask basically what is the maximum directivity. So if you think about it here, okay, what is the radiation intensity in the maximum direction, which is a little bit above the ground plane in these cases, and then normalize with the total radiated power. What do you get there in these cases? So is it the same 2 times or is it half? So let's do that as a new of these poles that sits there. So what do you think? A, B, or C? The same 2 times or half? It's very equal. It's 1/3 of each at the moment. So a few more votes. Again, we have actually equal results, 1/3 on each at the moment. So give me a few one more so we can see if we can get a winner. And then I will stop this. Okay, I stop it. So that was the result. Very equal distribution in these cases. As many votes for the same as for 2 times as for half. And of course, only one of them is correct. So if we see what actually is happening in these cases, what you have in this situation is of course that the radiated field, if you look at the E field above here, and you look at the E field there, they are the same. If you had the dipole, you would have the same E field down here, but for the monopole, the electric field below the ground plane is 0. So if you now start thinking, what was the directivity? What is D? That was that we should take the 4 pi, and then we should take the radiation intensity, and then total radiation here, P rad, maybe I should write. So I should take the radiation intensity, I should normalize it with the total radiated power. So if I have the electric field above here, so let's say we sit in a point up there. So I sit somewhere here or here. From the dipole and from the monopole, I have exactly the same electric field, which means that U is the same for these two. U monopole is the same as U dipole. What happens with the total radiated power? Is the total radiated power the same for the monopole and dipole? How did you determine the total radiated power? You took your radiation intensity and you added up all of it. Every radiation intensity everywhere, you just add it up. So if you think you add up the radiation intensity above the ground plane, so you take the part that sits there, you only sum up radiation above the ground plane. These pieces here, those two are the same because the electric field is the same above the ground plane. Do you get any contribution of the monopole when you look at what's radiating out down here? No, you don't get any radiation down there because your electric field is equal to 0. So you don't get any contribution below the ground plane. But of course, if you look at the dipole, here you have a large contribution. You have a lot of power that goes out there, as much as goes out up here. Which means that the total radiated power of the monopole is actually half of the total radiated power of the dipole. Again, we say that the currents are the same on them. And then I normalize with the radiated power. And that means that the dipole here has 2 times the directivity, or the monopole has 2 times the directivity of the dipole. So the directivity has to be the double for the monopole than the dipole. You go up a factor of 2. And that's because it doesn't radiate down here. The radiation below the ground plane is 0. So you have to normalize with a different number. So you get more radiation. So the directivity above the ground plane is 2 times the dipole, and the directivity below the ground plane is 0. That is what I had written on the wrong place for the folded one. It should be written here instead. So the directivity in this case is precisely here in some ways 2 times the dipole, and here directivity is equal to 0 for the monopole, because there is no radiation below the ground. If you do the same now and you look at the input impedance, what's happening in this case? The input impedance in this case will be the voltage divided by the current. That is the impedance. And if you look at the monopole, yeah, you have these ones here. So you have the voltage from the ground plane to the conductor divided by the current. But what do you have in this case for the dipole? There you actually go in the step that goes all the way from the lower part of the metal to the upper part of it. And that's twice that voltage. And that means that the input impedance of the monopole is half the input impedance of the dipole. So you just got half of it out. And as you can see, these are very simple relationships, fairly simple to understand what they are, and they're actually very, very accurate. So when you go from the dipole, you double the directivity, but you take half of the input impedance. And you can, it's sufficient to know how your dipole is working to understand these cases. So that is properties of your monopole. And then if you look at the radiation pattern of it, if we draw the same thing, you have your donut shape down here. So here is your typical dipole. And above these ones, you have then the monopole that sits there. And you can see here, the values are, of course, going down to approximately a little bit above 3, if you would take the half wavelengths. So 2 times 64. So like 3.28, 28 in that case. If you make it quarter of a wavelength monopole, which corresponds to the half wavelengths dipole. So that is the length that sits there. And the radiation pattern here, of course, in these pieces here, above the ground plane, these two are equal. But of course, below the ground plane, the monopole doesn't radiate, so there is no radiation below the ground plane. And that's why you push up the directivity when you go from the dipole to the monopole. So the monopole is a very good practical antenna. And it's basically half a dipole.
Yeah, I have a question.
Yeah.
So how does the effective area changes between monopole and dipole?
Yeah, in the same way as in that case, you have that, let's say the losses are low because it is the gain instead of the directivity. The effective area of the antenna is again proportional to the gain, which would be in a lossless proportion to the directivity. So it changed in the same way, it will be double in that case. And there you have to be a little bit careful because now it can only radiate above it. But it's same proportions as it's between them.
So only the physical area has changed, but the effective area is doubled.
Yeah, the physical area doesn't change at all between them. And you can make an interpretation of this. If you think what's happening here, you have your monopole here. And the effective area is that it comes in a wave to it. And of course, this wave can now come down and hit basically the ground plane and get reflected up. That's one way of thinking about it. And one part goes direct to it. And in some ways, you can absorb both of them. That is one simple picture. And the one that comes to the ground plane is the one that would hit the image currents.
Okay.
So they are changing in these cases. Okay, so that was one way of now making our dipole antenna shorter. And we gained a factor of 2. So if you think you would make this Warsaw Tower, okay, you do monopole instead of a dipole. It's not exactly what they were doing, Yeah, you gain a factor of 2 then, and you could say, yeah, I can make it like 300 meters instead of 600 meters. It's still ridiculously long. The same thing if you were thinking about taking your cellular phones, you have a 700 band there, which of course is around 40 centimeters of these cases. Yeah, you can shorten it down, but it's still large. It's too big. So in all of these cases, we actually would like to make them smaller. And there are quite a lot of tricks to make these antennas smaller. So you would like to have a similar radiation properties that should radiate like a dipole if they are standing in basically free space. If they're above a ground plane, they should radiate like a monopole, but they should be smaller. So we need to shrink them. And some ways of doing this is, for example, add an inductive loading. Why would an inductive loading be good for a dipole antenna? What I mean by loading is that we basically add coils to it. And if you think about your dipole antenna, when you make it very short, it was capacitive. If you want it to be self-resonant, you can add a lot of inductance. And if you add a lot of inductance to it, you can compensate the capacitance of the dipole antenna with the inductance of that loading. And you can lower the, the resonance frequency. And that's a circuit way of doing it in some ways. You can do something that's called capacitively top loading. So you start in this case adding things on the top here. And that actually lowers the resonance frequency of these cases again. And the numbers that you can see here is that this is what's called electrical size of it, Ka. And what that measures is how big is this if I put a sphere around it. So it fits within the sphere. And the radius here is, in that case, the radius of this circumscribing sphere. And K is then the wave number. So Ka is then that radius divided by the wavelengths and then 2 pi between them. Half wave dipole is 1.5. So by adding this loading here, I went down to 1.2. Adding even more, I went down to 0.63, which is more than a factor of 2 at least. So I can shrink it in some ways. Yeah, some of the loading here, 0.93 in this case. And then we do for another version of this, which is called meander lines. That's it. And here you can see the first one, it actually went down to 0.48, which is a factor of 3. And now we're talking, now it gets a little bit more interesting. A factor of 3 is not too bad. So if you think about your cellular phone antennas, if a half wavelength, that would be like 20 centimeter, and then you do a lot of foldering, yeah, then you're down to like 7 centimeters. And actually start fitting inside of this kind of devices. So you start in some ways playing around here with these structures. And what you do with the meander line here is basically that you increase the length of the wire. Because when you think about your antenna, what's interesting if you want to fit it somewhere is the height here. And of course, the width in these cases. What is interesting for the antenna to work is actually more the length of this wire that goes around there. Because it is that way that the current has to propagate. So you can take your half wavelength antenna and start bending the wire. It fits on a much smaller scale, but you can still get effectively like the same length of it. It's not exact, but it's approximately there. And now you start shrinking your dipole antenna. It will not affect the, the radiation pattern out of it. It can lower it a little bit from half a wavelength one, and it will get closer to this Hertzian dipole. But that's a small effect. It does change more the effect of radiation resistance, because you studied it before, and we computed the radiation resistance for a short dipole, and we realize it's very low. That means that these antennas here have a fairly low radiation resistance, lower than half a wavelength dipole, for example. And in many cases, it's too low for 50 ohms, which means we need to increase that one. And then we can ask, how do we increase the radiation resistance? Then we go back to the beginning of this lecture. What did we do? We did the folded dipole. And then we can do folded meander line antennas, which are folded, shortened dipoles. And then we can push it up again. So this is a typical meander line. And this is FECO simulations. The data is on Canvas, so you can download it. You can see the current that you have in these cases. You can see here the current points in this direction, here it points there, here it points there, 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 and here it points there, and there it points there. Which means it's not so different from just taking one dipole and just put all of this at the same place, and it radiates like a dipole, because the currents goes in the same direction. And then you get the other effects, which is these currents. But here you can see that they go in opposite direction, every second one of them. So basically the green one here sum up to something that's closer to 0. They cancel each other. And the reason for this is that the total distance here, that one is basically less than lambda over 2. Because the full wavelength dipole would be lambda over 2 approximately. And now I have made the wire that length, so I make it shorter. So I get a dominant radiation from a dipole. It looks like a Hertzian dipole. If you will calculate this and you calculate the length of all of those ones, you can actually sum up the length here, and you can see that this antenna in this case is resonant here when L is 0.64 lambda instead of 0.5, as you will believe. But it's quite okay. You start changing the shape, and of course you will get different effects that comes in there. But as a rule of thumb, it's not so bad to say approximately half a wavelength. And then you have to adjust it, and that you can do in FECO or simulations. The bad part with this one is what you see here. So by shrinking that, it starts looking like your Hertzian dipole, because it behaves the same as your Hertzian dipole, which you have computed. You computed the radiation resistance from that one. And if you remember, you get very low numbers on that one. This is slightly longer, so it will go up a little bit, but the general trend is there. When you make it shorter and shorter and shorter, your radiation resistance goes down. And then again, how should I push this up? What do I have to do? What is one trick to do it? It is to make a folded meander line antenna. So I can take this one and I can fold it and I create a new antenna. And this is a folded meander line antenna. And if you see what's happening in these cases, you approximately got up radiation resistance a factor of 4. Same idea as I described with the folded dipole. Because you get 2 times the radiated field, you get then 4 times the radiated power, but the current here that you use in the feed, let's say you feed this element here, is the same in those two. Which means that your radiation resistance will go up a factor of 4. And now you can see you can start playing with it. You could shrink it a little bit more. And of course, if I would like to, I could get this to 50 ohm by designing it. But I need some of these tricks to be able to play with these antennas. I need to compensate for different things, and I need to pay a price in many cases when I do this. But again, foldering is one of those actually very good ideas to increase radiation resistance when you start shrinking your antenna. It's not the only one, but it's one that is really good. We can look at the inductively loaded antennas. So we could say this, putting a coil there can be good. And in these cases, of course, if you put a coil, you can ask, should I put the coil close to the center? Should I put it in the middle, or should I put it in the edges? What does it affect in these cases? How will it affect the resonance frequency? What do you think? Approximately, will it change this? You can think in a few different ways. If you think it's mainly the length of the wire that will affect this in this case, does it matter then where I put this coil? No, the wire length is the same. Which means if I do this kind of quite coarse coil in this case, where it actually is the wire length that comes in, it shouldn't change the resonance frequency. This one should not change. So it changed very little. What can happen with the bandwidth? We have not studied that in detail, but we had learned one thing, that was fat is good. Not is only good to eat sometimes, it's actually good for the antennas. And what I mentioned there is that the most important part of that was actually that you wanted separation of charge. So you wanted plus charge there and minus charge there. And if you think about that, of course, this last one has to be the best, because here I get a large separation of the plus and minus charge. If I do it in this one, then I have plus charge there and minus charge there, and they are closer together. I would like to separate them as much as possible. And that would actually say here that in these cases, the last one should give the highest bandwidth. That is one way of arguing about it, at least. And if we see what's happening in these cases, we simulate this, run it in FEC or similar. If you look at the resonance frequency here, yeah, you can see it change a little bit, but it doesn't change much. It's a second order effect in some ways. But the radiation resistance is changing. So C here has much higher radiation resistance. And the same way, when you look at the bandwidth, you can see that C here has the highest bandwidth. And that is due to these cases that you actually get this separation of charge inside. So we can actually understand that without simulating these cases. We can just look at the basic physics of them and understand how they should work for these cases. So resonance frequency, not much change. Bandwidth, it increases as the coil moves away, and that is because you get increased what's called polarizability, which is that the charge separation gets big. That's what you would like to have there. And one way of looking at it is that you can actually determine what the charge is. And if you take a picture of them, you can see the last one here. Basically have a lot of plus charge there, and you can have a lot of minus charge there. So you get a huge separation between that one. And what you have is the length times the amount of charge that's separated. That is actually proportional to the bandwidth that you get. So that you can get out for these cases too. Okay, so that was a little bit general things about how we can change the dipole antenna. And now comes a few very important parts of this. When you start thinking about designing your antenna, assume that you have designed an antenna for a certain frequency. So let's say that you spend quite some time here to design your antenna for a frequency F1. So you've done, for example, your dipole antenna here, and you really know that this works very well for that. So you have determined that you should use a certain length there, a certain width in these cases, and you should fold it around. You did it for 1 gigahertz. And then your manager or boss comes down and say, okay, you need to do one for 2 gigahertz instead. Sorry, it should not be 1 gigahertz, it should have been 2 gigahertz. We changed the frequency. What do you do then? Do you just get angry for a while and then you start working again? Or you just say, sure, I fix that in 5 minutes? What do you think? If we think about all of these things, and what I've said many times here is that the performance and the antenna doesn't really depend on the frequency. It only depends on the wavelengths, and especially the relationship of the dimensions measured in wavelengths. That's where we talk about half wave dipoles, half a wavelength long dipoles. So that means that you can only measuring it in its own wavelengths. So if you have an antenna designed for 1 gigahertz, you want to have it for 2 gigahertz. And if you're allowed to change all dimensions, it's trivial. You make the antenna half as big. So what you can do is that you can scale all dimensions here with a factor which is F1 over F2. And that means that if you had it for 1 gigahertz, you want to have it for 2 gigahertz, then it is 1 over 2. So you should make all dimensions half as big. And that's really what's happening for antennas. In some cases, of course, you're not allowed to scale everything. Then it's a little bit harder. But the basic idea is just look at how big your antenna is in wavelengths. And if you want to have it at another wavelength, just take the quotient between those wavelengths and change all dimensions. It's valid as long as your materials do not depend on the frequency. And in the microwave range, like gigahertz, that is in general true. It's not true when we go to optical antennas, we will talk about later in this course. There the material starts depending on frequency, makes it harder in some cases. So if we take these ones and we say that you have a dipole with length 1, and as I said, it's resonant for F1, new dipole have then L2, which is L1, and the quotants of the frequency. And that means that the scaling is in the wavelengths. So L1 over lambda 1 should be same as L2 over lambda 2, which means that when you measure your dimensions of your antenna, you measure them in the unit of wavelengths. Then everything is simple and trivial. That is your natural way to measure the size. And what I assumed here is, of course, that the materials are what we call non-dispersive. They do not depend on frequency. And I also mentioned it that this is not true for what's called optical antennas. When you go to visible light, for example, in general, materials change their properties very rapidly around optical frequencies. So if we take a case here and we say that you have designed your antenna now for 1 gigahertz, it's resonant. You want to design it for 2 gigahertz. You have your meander line antenna here. How should you scale all your dimensions? How big should you make it in these cases? So the first one, you can see it's 10 centimeter long, it's 3 centimeter wide. And we will start a poll of this. So either you should make it the same dimensions or 5 centimeters or 20 centimeters. What should you do in these cases? So if you do this, A, should it be the same dimensions? B, should length be 5 centimeters and width 1.5, or should it be 20 centimeters and the width 6 centimeters? What do you say? I basically told you the answer on the previous slides. How big should you make it? So we got in 50% of you, a few more votes. Okay, so let's end the poll here. So here you can see the results. So at least B won. You should make it half the size. There were a few arguments that you should keep the same dimensions in A, and that's of course not good. If it's resonant for 1 gigahertz and you want it for 2 gigahertz and you keep the same antenna, you have to be really lucky if it should work at other frequencies. So in all of these cases, you should just use this scaling laws. And this is, again, one of those cases where you can see it's really good to have the idea of, for example, 1 gigahertz, 30 centimeters. Okay, I want it now at 10 gigahertz. Okay, that's 3 centimeters. And you scale your antenna with this number of the wavelengths. That is how you measure it. So if you made an antenna and a dipole antenna for 1 gigahertz, you want it for 2 gigahertz, just make it half the size. And in many cases, maybe there is a ground plane or dielectric thickness of some slabs, you cannot change it. Then at least you have your initial design done. And then you can optimize around that one. But it says in all of these cases, we really talk about antennas and the dimension measured in wavelengths. That is the natural way of looking at the dimensions for antennas. And scaling is then really powerful to change these things. You will see it when you make your patch antenna, you start measuring that you have the wrong resonance frequency, which means you should scale your dimensions, which means you scale everything with a quotient between the frequencies. One is the frequency you would like to have, and the one is the frequency you actually have of the resonance frequency. You take the quotient, and that tells you how you should change your dimensions. That is what you should do in those cases. Okay, and if we of course do it in the opposite way, so 500 megahertz, it should be the double size instead. And if you do it even further down, a factor of 10, then it starts to get 10 times the effect of this one, and you just scale it on. So if you have one of those designs, you can do every design. And it's valid for basically all antennas. It doesn't have to be a dipole. It works as well in this like meander line structure or patch antenna and so on. It works for basically all of them. Just scale all dimensions. Okay, the last thing we'll go through today is really the freeze transmission equation. And I told you before that we will generalize these ones. So that is what we will do now. And you have already done it on your exercises. So of course, the freeze transmission equation is really basic to say how much power is transmitted from one antenna to another antenna. So you have here one antenna with some quantities, the transmitted power, the gain of the transmitter, and the effective area of the transmitter. And in the receiver, you have the same parameters for the receiver, and then you have a distance between them. And then you can derive this freeze transmission equation. Of course, you can memorize it, you can know it by heart, you can look it in the formula sheet, you can look it up on internet, you can do it anywhere. But actually, this equation is so, what to say, fundamental and actually simple that you can derive it. If you don't have the formula sheet, you can actually derive it yourself. You can take it out, but you need to understand the pieces that sits inside of it. So if we say what we would have here, and we say, I would like now to determine the received power in these cases. How do I do that? Yeah, what I'm saying here in the first case is that then it comes some P in here, some incident power density to that antenna. I don't know what it is from the beginning, but there is some power density that comes to this antenna. How do I get the received power? I have to multiply it with effective area of the antenna. So the received power is the incident power density times the effective area. That is the property I have done. That's the received power. And what I need to do afterwards is to rewrite these two quantities. So I need to rewrite what P in is and what the effective area is. And by rewriting those, I have freeze transmission equation. That is all there is in freeze transmission equation. So in the first case, what is the incident power density? What is that? Yeah, that is from the transmitter. It has something come out here, which is this U that goes in different directions. So I need to have the radiation intensity of these ones divided by the distance. That is the incident power density. Maybe I said radiation intensity before. So P in is the incident power density, watts per square meter. And that is the radiation intensity divided by the distance squared. And it decays as distance squared due to this divided over this spherical area, and the area increases as R2. So I can rewrite P in as U over R2. I have again the effective area that sits there. And then I can rewrite the radiation intensity and the effective area in the parameters of these antennas. And if I do that, first the radiation intensity that sits here is related here to the radiated power, the gain, and then 4 pi. That is the definition of gain. That is pure the definition of gain that sits there. And in the next case, I have the effective area, which is related to the gain of the receiver. And if I plug that in, I have my freeze transmission formula. So that is the one that you used so far, where we say it is the product of the gains, lambda squared, transmitted power, and then divided by 4 pi R2. And in this case, maybe a simpler way or sometimes more understandable way of writing it is that, of course, what comes in here with this lambda is that we measure distance in the same way as we measure antennas in the number of wavelengths. So it decays with the number of wavelengths the wave have to propagate. And now we will then generalize this equation. So when we do that, we add the other parts as we have introduced in the course. So we already introduced the mismatch. So if you have the gain of the antenna, that is related to the accepted power of the antenna. If you have a mismatch, what comes in there is that you have to take 1 minus this reflection coefficient squared. That is how much your accepted power is reduced. The same thing happens at the receiver. So you have to reduce that one too. And you can have a polarization mismatch, which means that one antenna, points like this, and the other one points like that. They are not co-polarized, these dipoles. It should be like this. If they're like this, they don't work. And now you have a freeze transmission formula that includes also these cases where you can have mismatch in the antennas. And that means we just have to add these terms that sits there. We add that to the freeze transmission formula. And this, of course, is now radiation in free space. If you would go in these cases to complicated channel model, yeah, then you have to add that part. But that we deal with in different courses. So this is then the effect we have when we add it to the freeze transmission formula. And that means that when we do this, we actually get different parameters. I will just do this quickly before we break. We will talk about the lab on Monday instead. So we have before introduced gain, and the gain was the radiation intensity normalized with the average radiation intensity. So the total radiated power and 4 pi. And now I add a few more factors that actually comes in a system perspective of this. And the first one is called realized gain. So the gain is really a property only of this metal that sits on my antenna. It doesn't care really about the connector and the feed. If I add the realized gain, then I start caring about that one. So that includes the mismatch to that one. And that is called realized gain. The next thing is that I don't care about the polarization when I talk about gain. If I start caring about polarization, I get what's called partial gain. So that is the gain, for example, in this polarization and the gain in this polarization. They have different gains when I go to the partial gain. And of course, if I have a realized gain and a partialized gain, I have a partial realized gain. And that is the most accurate way of describing these antennas because it includes the mismatch and it includes the polarization. That is partial realized. And one example that we will skip of this today here, but you can look at the factors of this partial realized gain. And an interesting thing in these examples, you will actually do it also in the exercises, is that when we look at the received power here, this is the freeze transmission equation, you have one transmitting antenna, one receiving antenna, and I start changing the length of it. And one is then at the peak of this, one is in the middle, and one is the next peak. And of course, when you are at the peak of it, it's perfectly matched. You can calculate then how much power you receive. And when you calculate that, you get 15 microwatts. When you actually sit in the middle of this, where it's totally mismatched, in this case, you will receive 1.9 microwatts. So much, much lower, but actually not that much. It's like a factor of 8. And a factor of 8 in power you can actually live with sometimes. And that means that you can actually receive things in this antenna even when it's mismatched. You don't suffer a lot from it. And then, of course, you can make it longer, then you get a little bit more. You will do this in one of the exercises. So I skip it here, and we will go to the conclusions of this, or the summary. So what we've done today is really to see that the understanding that you have got in this course from the first lectures of the dipole is useful for a large family of antennas. The folded dipole was one version where we looked at, in some ways, 2 dipoles. And we don't have to do any new things. We can actually understand it from what we know from the dipole. Exactly the same for the monopole. It's like half a dipole. And if we understand the dipole, we understand the monopole. The shortened dipoles here are slightly harder. And they go to this case that we can understand the radiation properties because they are the same as the dipole. But to really understand the resonance frequency and the details, in those cases, we really need to go to numerical solvers. So those we will analyze in numerical methods. Typically in these cases, these finite method of moment simulations, for example, in FECO, where we can actually simulate those. We will stop with this, and then I will keep this part and actually go through the laboratory sessions on Monday instead, where we will talk what's expected from you. And that is also the time where we go through the antenna that you would need to do in this laboratory session. So we do that on Monday instead. So with that, we will then end this lecture. And